4.2 is solving by graphing. We'll also do it with calculators and Desmos. Quadratic equations with two variables can't be solved with one variable method. So we can't just try to get x by itself. One option that we have, however, instead of trying to solve it just with straight algebra, is graphing it. If I think about this equation, x squared plus 4x plus 3, y equals x squared plus 4x plus 3. Well, that graph looks like this. And it turns out that a graph is like an infinite guess and check mechanism. Like everything on this purple curve is some input and some output from this equation over here. So for example, if I thought, okay, if I plug in a 1 for x, I'm going to get out what looks like an 8 for y. If I plug in a negative 2 for x, I get out negative 1 for y. If I plug in negative 4 for x, I get out 3 for y. It's like an infinite guess and checker. It's also like a visual picture of a table. The table is also kind of like a guess and check method, where you plug something in for x, like negative 1, and you get something out for y, like 0. So this graph shows every possibility of x squared plus 4x plus 3. We want to find the exact cases where the y value is 0. We want the y value to come out to 0, and that happens here and here. So if x is negative 3, or if x is negative 1, we have our solutions. Those 2 points solve the equation. And it can work for any number, like it doesn't have to be 0. This is the same function over here, x squared plus 4x plus 3, it's the same, but now I want to know where does the y value equal 5 instead of where does the y value equal 0. This is the y value I'm checking from this function over here. Well, that happens here and here. So it's like if x is at, I don't know, about 0.4 and negative 4.4. So we can just check this by plugging it into a calculator, which we can do quite easily. I'm just going to take negative 4.4 and plug it in for x. So there's negative 4.4 in parentheses squared, plus 4 times negative 4.4, plus 3. Well, that's 4.76, pretty close to 5. Not actually 5, but quite close. So had I done like 4.45 or 4.5 or something in that range, I could just keep guessing and checking to get closer and closer. But that's how you solve by graphing. You graph the equation, the whole equation, with a y equals instead of a number equals, and then you find what y value matches the number you're looking for. You know what, we've done this before. This might feel kind of new to you, but it's actually something we've done before. We did it with piecewise functions. If we have f of x equals 3, well, here's our function f of x. We're basically solving the equation, where does this equal 3? Where's the y value 3? And what we did is we said, okay, this means the y value is 3. Well, that happens not there, here. That's the one place where the y value is 3. The x value is 1. We really just solved the equation 2x plus 1 equals 3, because f of x was really 2x plus 1 in this case. There's 3 possible pieces. In this case, it's 2x plus 1. When does it equal 3? It equals 3 when x equals 1. So what if the y value is negative 4? Well, that happens just right here. That's if x is negative 2.5. And what if the y value is positive 4? That happens here and all of here. So that's if x is negative 4 and 5 or greater. So we've done solving by graphing before, we just didn't think about it this way, but it's the same thing with these quadratics. So I'm going to solve 5 equals 2x squared plus 4x plus 1 by graphing. I'm going to graph y equals 2x squared plus 4x plus 1. Now remember, my a value is 2, my b value is 4, my c value is 1. So the y-intercept is the point 0, 1, so it's always at c. Whatever that c term is your y-intercept. I want to find the axis of symmetry, which is negative b over 2a. That's what x equals. It's a vertical line. That's going to be at negative 4 over 2 times 2, which is at negative 1. So then to find the vertex, I do f of the AOS, which is negative 1. F of negative 1 becomes negative 1 squared is 1, times 2 is 2, minus 4 is negative 2, plus 1 is negative 1. So I've got a vertex here, an AOS here, a y-intercept here, so I have a symmetric point here. And now I can just make a table for a few more points to finish off this graph. So I'm going to put the AOS in the middle. I have these, so I'll plug in a 1. Plug in a 1, you get 2, 6, 7. And it's symmetric, so negative 3, 7. the graph goes like this. I can't fit anything else on this plane. That's okay, because I only had to check 5. I want to see where's the y value 5. And that happens here and here. Now here's an important thing to understand about the symmetry of these parabolas. The distance here from the AOS to this point has to match the distance here from the AOS to this point because it's symmetric. So I'm going to have to estimate a decimal here, but whatever decimal I estimate on one side has to match the other. So I'm going to call this looks like it's the point 0.8, comma 5. Well, that means this has to be negative 2.8. Because it has to go 0.8 in both directions. And that might not be perfect, but it's going to be pretty close, and probably close enough. And again, we could check this quite easily. I'm going to plug in negative 0.8, or sorry, positive 0.8 for x. 2 times 0.8 squared plus 4 times 0.8 plus 1. This should come out to something very close to 5. Yeah, 5.48. So 0.8 was too far. It's probably 0.7 or 0.6. Somewhere in that range. But that's me solving this thing by graphing. And we can solve it for any value now. Like if I wanted to know when does 2 equal 2x squared plus 4x plus 1. Well, I'm just saying the y value is 2. That happens here. There's a y value of 2. And there. So like 0.1 and negative 2.1. And if I asked, where's the y value? What if we did like negative 3 equals 2x squared plus 4x plus 1? That never happens. The graph never crosses negative 3. This has no solution. So you can see that from the graph also, because this has a minimum value at negative 1. Anything below negative 1 is not going to happen. Anything exactly at negative 1 has only one solution. Anything above negative 1 has 2 solutions. And remember, a graph and a table are essentially the same thing. They're both showing the same points of information, just a graph does it more fluidly and more visually, but a table does it more precisely. We can see actual points. If I wanted to find roots or zeros or x-intercepts, remember those are all the same thing, where the graph crosses the x-axis, I can look at a table and see on the y values, when does the sign change? When does it go from positive to negative, or from negative to positive? Because when the sign changes from positive to negative or negative to positive, that is where you're crossing the x-axis. Because here the y values are positive, here they're negative, this point and this point has them at 0. So I can look at a table and say, okay, this is going to have roots somewhere between negative 2 and 1, negative 1 I meant, and somewhere between 0 and 1. And I'm writing these like points, but this is supposed to be interval notation. So maybe I'll do it in the brackets. It's really between negative 2 and negative 1 and 0 and 1. The roots are somewhere between those two x values. And over here, the roots are somewhere between 0 and 1, because that's what these x values are, and somewhere between negative 5 and negative 4. But it doesn't have to just be roots. I could also say, okay, where's the x values, where are the y value equal to negative 3? Where does y equal negative 3? Well, that's going to happen somewhere in this range, so between negative 4 and negative 3, and somewhere in this range between negative 1 and 0. Okay, last one here. We're going to graph y equals negative 2x squared plus 60x plus 12. Now, this has a pretty high y-intercept compared to what we've been doing. I mean, the y-intercept is 12. But it also has an AOS at negative b over 2a, with negative 60 over negative 4 is 15. So the AOS of this is 15, which means the vertex is going to be probably a pretty large number. I do f of 15, and I don't want to do that by hand or in my head or anything. So I'm going to do negative 2 times 15. Come on, Grant, turn this thing on. For the record, my name is Grant. Now you know the secret's out. Also, if your name is Grant, I'm sorry I wasn't yelling at you. I'm the one messing up, not you, Grant. You're doing just fine. I assume. Maybe you're not. I don't know. Ignore me. Just, keep doing your thing, Grant. We gotta stick together. 462. The vertex is 462. Well, I don't want to graph that by hand. And I don't know if there's any value to me graphing that by hand, because I'm not going to be very precise or very accurate. It's going to be a bit of a mess. So let me graph it on here. I press the y equals button. Y equals negative 2x squared plus 60x plus 12. I press graph, and that's not super helpful. And I can see that like something here graphed a little bit, but because this graph is so big, having a window that's going from negative 10 to 10 on the x's and the y's, you know, this is going negative 10 to 10, negative 10 to 10, isn't showing me the stuff that I need. The AOS would be like all the way out here at 15. The vertex is going to be way, way up off the screen at 462. I've got to change the way this looks. So just typing the equation into your calculator will often not be enough. You have to actually have some idea of what size you're looking for. That's where knowing the AOS and the vertex first is very, very important and helpful. Now I know that the highest point this graph reaches is 462. So I'm going to have the y values go to 500. So I'll have them start at negative 50, and I'll count by 25s, just because why not? I like to get some space above and below, and count by 25s so there's not a ton of hashes. Now for the x values, since the AOS is at 15, that's not always exactly halfway. In fact, it's pretty rarely halfway. But it can be a good estimate. So my guess is like if I go out to 30 or maybe 40, that's probably enough. I'll go out to 40, and I'll have that count by 5s. And now if I graph it, that's a good looking picture. That's something I can work with. Notice how I have space on both sides. I have space above and below. I can also see where the intercepts are. That's very important. I can see the vertex. And I knew the graph was supposed to be going down. That's such an important check. The a value is negative, so the graph is going down. Now you'll notice at this point I can't tell when it equals 5 or 50. I'm trying to make this equal 50. And I could like, you know, try and like 50's here, so it's going to be like there and there, but I can't really do that. You might be tempted to try and go to this menu, the second trace, and like type in value. But value is just a guess and check. If I plug in 1, I get out 70. If I plug in 0.5, I get out 41.5. And the guess and check can be kind of useful. The table does the same thing. You know, you can scroll up and down, or you can go to second window and change your table setup to where it's ask, letting you plug in numbers. And you can plug in like 0.1, 0.2, 0.3. You know, you can guess and check your way that way if you want to. However, the best way to do this is to actually make two graphs. On top, I graphed this part. On the bottom, I'm going to graph this part, just y equals 50. Now it draws me a line at y equals 50, and I can find where these two graphs cross. So I'm going to do second trace, go to intersect, which is the 5th option, and it says first curve. That means which graph do you want to be on. You can just press enter. Then it says second curve, in which graph do you want to be on. It's going to jump to another one, press enter again. Then it says guess, ignore that. And it gives you the intersection to the right of those 2 points, 29.357. Good, there's one of them. I've got to find the other one. So to find the other one, I do it again. I go to intersect, and now I want to scroll all the way to the left side of this intersection. And you'll notice, based on my window, I'm just tapping left over and over and over. You can't really see it, I'm just tapping left over and over. You'll notice the spider's going to go off the screen. I can't see it anymore, but I know my y value is low enough. It's below 50. And that also means that I'm to the left of it, because I'm at a negative x value. So I press enter again, press enter again. The other one is at 0.647. So that's how you can find the intersections with your graphing calculator. Remember, these have to be the same distance away from the AOS, which was 15. And this is 14.37, and from here to here is 14.37, so from here to here is 14.37. This is all working out quite nicely. Of course, Desmos can do the same thing. What was my equation? Negative 2x squared plus 60x plus 12. So I'm going to go negative 2x squared plus 60x plus 12. Negative 2x squared plus 60x plus 12. Again, this window is not very helpful, so I have to, and I can zoom out, but zooming out isn't that great either, because what happens is your x values get really, really narrow. And yeah, if you're on your iPad, you can like touch and pull and stuff, but I'm on my computer, and I'm going to change the window to be basically the same. The x's are going to go from negative 10 to 50. I'll have them count by 5s, and the y's will go from negative 50, and what did I say, 500? Looks like 500 is going to work. Boom, there we go. Now I want to see where's the y value 5. Well, I could just kind of scroll along here until I find that. But what's better, no, sorry, 50, not 5. And I could just sort of like, yeah, it's tough. I can make a new equation. Y equals, or just type in 50. No, sorry, I want y equals 50. Y equals 50. Now, oh, I bet it was showing it the whole time anyways. Yeah, now it shows me this. And I can tap this and say, oh, it equals 50 at 0.647 and at 29.353. And the really nice thing about this is I can change what y is and find different solutions. I can even type in something else up here, like, let's say 200. Where does this equal 200? Well, that happens here and here. I hope you're seeing the value of this. You can solve any equation this way. Type in the two pieces that you want and just go for it. So there's solving by graphing. Incredibly useful, especially with things like graphing calculators and Desmos. Hope you have a wonderful day. Hey, you did it. You watched a whole math video, or you at least skipped to the end here. Either way, thanks for watching. I hope it was helpful. If it was helpful, maybe share it with a friend in your class who could also use it. You can subscribe to follow more videos. You'll see links popping up on the corners to watch previous and past and good videos. You can always leave a question down below or just add a comment, and I hope you have a wonderful day. Thanks for watching.